to another video. Um, Today we're going to be doing approximating volumes of solids by integration, and we're going to be talking about two things. We're going to be talking about the washer method and the cylindrical shells. Two different ways that we can approximate the volumes of solids, and this is going to be building on our last lesson. So this was just my class right here. Yep, that was a lot. Okay, but last lesson we were talking about how we split shapes into shells like this, into little slices. And then we do that. And it's using that idea of that, the fact that the integration symbol is just a summation, it's just summation, and then dx we can think of as a unit of length. So if you guys haven't seen that video, or if you've forgotten that, if you don't know how to do that, and when I say you guys, I mean myself, because I'm gonna forget it. So that's why I'm making these videos. But if I've forgotten this, I could look at that video first before looking at this one, because this one's explaining the different methods, and this builds on that. Okay, so let's talk about the washer method first. So the washer method, and we can look here, you guys are going to learn how to do these equations here, learn how to use the washer method, and the washer method's used for something like this. And we're going to use cylindrical shells. This is the equation, if you just need the equation because you forgot. And this is the circumstance where we're going to do here. Notice that this is the axis of rotation for this one, and this is the axis of rotation for that one. So now we're looking at the washer method. Why is it called a washer? Well, a washer is something like, it's like a it's like something like this. Very thin piece of metal. And what it's used for is it's put against bolts. So that's why they call it a washer. But what are we going to use this washer for? Well, the washer has a shape like this, right? Remember last time when we had a sphere and we cut it into little slices like, like this, where each one is a square cylinder, right? That's how we can do integration with it. Well, the washer is for circumstances where there's a sphere with like a hole in the middle, for example, and then actually there's like a hole here, and it goes through the sphere, right? So for circumstances like that, we're gonna have slices that look like this. This is what the washer method is for. So remember how we had to find the area of each one, area 1, area 2, area 3, and we sum it up using this, or we can use the summation symbol, right? But the integration symbol, which is just a summation. So let's go through this again. Well, how do we find the area of a washer? Let's say that we had, can't change pens for some reason. Let's say that we had the center point here. This is radius R1. This is radius R2. How do we find the area? Well, the area will simply be the radius, the area of the outer circle, right? This much, right? And we're going to minus this area from the inner circle. So that's what we're going to do. So how do we say that? We take the area of the larger circle, which is pi r2 squared, right? That's the area of the larger circle, minus the area of the inner circle, which is pi r1 squared. And we can simplify this as simply pi all of that outside r squared minus r2 squared minus r1 squared. There we go. So that's the area. And then simply after we have tons of slices like this, that have thickness of, remember, this length is dx, that's the height, then we multiply by height and it should be there. So that's pretty simple. So let's do an example of um actually, I'm gonna do a quick recap of last week's lesson, and then I'm gonna do so. Let's say that we had a ton of washers. Let's say we had the scenario of that sphere with a hole that runs through itself, right? A sphere. This doesn't look like a sphere. God damn it. Okay. Sphere with a hole that runs through the sphere. So when we split this up, sorry if that looks a bit confusing. If we split this up, what we get is washers that look like this. So this is, let's say this is the outside, right? And then we have another piece here. And we have another piece here. We have another piece here, right? And then all of these, we're going to have the unit length dx. Remember, this is from the last video. If you don't remember, check it out. Dx. And then each one is going to have an area. So what we do is we sum right? And actually, let me ask you guys. So if we take this one is gonna look like this, right? If we zoom up, it's gonna look like this. I'm gonna make it bigger. So one of these washers, when we zoom it up really big, is gonna look like this, right? It's gonna look pretty similar to what we have there, just in 3D. So this is R1, and this is R2. And this is height, which is equal to dx. So how would we find the area of the cylinder, right? We need to find the area, sorry, how do we find the volume? Well, we first need to find the area of this face. Hey AJ, I'm making a video for myself to remember math, so I'm going to be narrating my math phone to myself. It sounds like a YouTube video, okay? Alright. Okay, so we need to find the area of this face, here, and we need to times it by the height, right? Which is dx. So let me delete all of these. So how do we do this? Well, we know the area of the face. Actually, I'm going to keep these in. Don't know why I deleted them. The area of this face is equal. Actually, the equation of the equation for the volume of a cylinder is what? It's area. It's actually, well, we just think of it as area times height, right? If we have the area of that face, we times height. Well, what's area? We found it up here. Area is pi r2 squared minus pi r1 squared, right? That's the area. Then all of this times h. So let's apply that to these slices here. Okay, so let me copy these slices down. Okay. So how do we find the total, right? If we have the volume of each slice. So now if we had the volume of this and then volume of this and volume of this and volume of this, what's the total volume of the shape? Well, it's the sum of all the volumes, right? The sum of all the volumes. Or we can express it more using the area is that we have the sum of all the areas of each individual piece multiplied by the height of each individual piece, right? And let's do this again. So the sum of each area, what's the area of a washer? Remind me, it's pi r2 squared minus pi r1 squared multiplied, that's the area, right? That's the area. Now we need the height. What's our height? Dx. Okay. So now if we instead of using the summation symbol, we use the integration symbol, well, and then that's simply the integration of, let's take the pi out of this, pi r2 squared minus r1 squared dx. There we go. And yeah, yeah. Okay, so I'll explain this in terms of a real example right now, but this is how we transfer from, the single washer here, and then we transfer it into an integration symbol, which then we can use as an equation. So let's try using on this example. This example here is, let me draw it out. We have y equals the root of x, square root of x, and which intersects with y equals x squared, right? And they intersect at some point, and we want to find the volume of this shape. And if you can imagine the shape, it's going to look like this, right? It's going to look like this when we fully rotate it. Let me draw the rotation of axis. Actually, I forgot to define the rotation of axis. Our rotation of axis is around the x-axis here, okay? And so if we imagine the shape of this, it's going to look like, so if we take this point here, right? Let me color code it. At this point here, we're going to trace it around in a circle. And then this point here, we're going, let's use blue for that one. This point here, which is like about here, we're going to trace it around in a circle. So we end up with a shape looking kind of like this, right? Oops, sorry about that. We end up with a shape looking like this. And then there's an inside slope here as well. So there's, if you imagine like, it's like this. That's one slice of it. I'm going to color in one slice. And this is on the, I don't think this is helping, but I hope you guys can imagine what this looks like, right? If you can imagine this rotated around like that. Oh, if you can imagine this rotated around like this. Oh my God, I keep doing that. Yeah, rotated around like that. That's what it's going to be. So that's what the shape we're dealing with. And if you think about it, a shape like that, where it's like this, is simply going to look like it's going to be like a washer. So this point here is the first part, right? Well, technically at zero, there's zero. And then the next part here is going to look like this, and there's going to be a hole in it. And then the next part here, it's going to be bigger, then the hole is going to be bigger, right? And then it's going to keep on making stuff like this. So we need to do the same thing here, right? So we need to be able to find the area of each of these washers, right? Area of each. So we need to find this area, this area, and then we need to multiply that by the length, which is just dx, right? Of the height, sorry, the height of each, which is just dx. And then we add all the volumes together, which gives us the total volume of the shape. So how do we find R, right? How do we find R1 and R2? Well, let's first define which one is R2 and which one's R1. We can see that y equals the square root of x stays on top of y equals x squared the whole time. Therefore, this is going to be the outer edge, and then this is going to be the inner edge. So we color code that again. This is going to be our outer edge. This is going to be our inner edge. Or if we look at it on our washers, our outer edge is around here. This is our outer edge, right? Which is just created by the rotation of the point along, each point here we rotate it, right? Which creates these washers. So that's what we're doing. Each rotation, I'm actually going to keep it on like this. Keep ink, and we're going to keep our rotations like this. So these are the different kind of like shapes, right? And then the green one, right? This one, and this length here corresponds to, let's say, this washer here, right? And this is the point, this is the kind of rotated point of it. That's just this point doing this thing, right? So we have that. So basically what we're saying is this is R1 and R2 is this at that same point. Let me make that more clear. R1, and let's say that these two arrows start at the same point. This is R2. So at any point x, y equals root of x represents R2, and y equals x squared represents R1. Does that make sense, guys? So let's say we're at like this point here, right, which is A. Then at point A, and let's say this is the washer at point A, right? This is point A plus, dx on either side, or like half of dx on either side because it's in the middle of dx. But if we think about it, point A, we're at point A, and what's R2, right? We need R2. R2 is equal um, R2 is just equal to x squared. Oh wait, no, root x is on top, so R2 is equal to root x. But instead of x, we put an a. So root a. Oh my God, root a. And then R1, which is this line here, which is x squared. X squared is just, R1 is going to be x squared, but then at point A, we substitute a in, so a squared. So yeah, that's how we find the radius at each point. So now we're going to set up the equation. Remember that it's just the summations of all these different washers. So how we're going to do that? Well, let's think about this. For any washer, okay? For any washer. What is it's going to be? Its area, right? Remember what we said. We have R1 in the middle. R1, the smaller one is R1. Oh my God, R1. And then the bigger one is R2. Therefore, the area of each washer, remember the area is just this face here, right? The area is just this face, is equal to pi R2 squared minus pi R1 squared. Remember, because we're just taking the bigger circle area minus the smaller circle area, which gives us this area in the middle. So we have this, the area is that. So remind me what's R2, guys? R2 is root x. Root x, let me just think really quick. Okay. Now let's think of it like this. Instead of doing what we do is to make a washer, to find the area for a washer, we can simply do this, or to find the volume of a washer, we can simply take this cylinder here, right? Which is the cylinder created by just y equals x squared. So none of this, right? Just y equals x squared. And then we also, we take this, we minus the smaller cylinder, which is created by y equals, sorry. The larger washer, larger cylinder, the larger cylinder here is created by y equals root x, right? This is created by a revolution along the point of y equals root x. And then it's minusing the point of revolution on that, the line of y equals x squared. And this together creates the washer that we want at any point, right? So then we end up with something like this. And we have this, oh my God. And we have this inner edge here. Why can't I close this? Okay. We have this one here. So that's what's happening. So what we have to do is using this principle here, right? This principle here, which is the same idea as this, but then we look at volume first. We can, what we could do is we could take the volume of any washer is equal to the volume. Oh my God. I don't even know what button is doing that. The volume of any washer is given by the where it's given by the volume made by what's it called? Volume made by what is it? Volume made by y equals root x, because it's on the outside, minus the volume made by y equals x squared. Okay, does that make sense? So we're just taking the larger circle minus the inner circle gives us this. And we just repeat it a lot, right? We just repeat it a lot. So let's do that then. All we have to do there, then if we think of the volume of all washers, right? Volume total of washers, which is equal to the volume of the whole solid. Volume of the whole solid is just the summation of volume of each washer, which is equal to the summation of the volume of all washers. Oh, wait, no, the volume of each washer. Sorry, not washer, sorry. This is equal to, if we think of the volume of the summation of the volume of each washers, then we need to find that is equal to the volume of the larger cylinder, each larger cylinder, volume of each larger cylinder minus the summation of the volume of each smaller cylinder. And how do we do that? Well, we do this, the summation of the area of each larger cylinder multiplied by what's the height? Remember that a cylinder is just the area times height. So what's the height? The area of each one, what's the height is dx, right? The height is dx. Remember the last episode? Then this one is the area of each smaller cylinder multiplied by dx. And then how do we write this out? Well, we just have to write it out in the sense that the larger area is given by the circling of the radius, right? The radius, and remember this radius, this is R2. R2 is the larger radius, and R2 is just equal to root x, right? R as whatever the x is. So the R2 at point A is root A, right? So R2 is just equal to root x, and then R1 is just equal to x squared. And I forgot to tell you guys that this intersects at 1. sorry guys, x squared where 1 equals x squared equals root x, right? And then we can square everything, x4 equals x squared, sorry, x squared equals x, um, and then x4 minus x equals 0. So x out of x4 minus 1 is equal, sorry, x3 minus 1 is equal to 0. So x equals 0, or x equals 0 is this point here where they intersect at 0, and x equals 1, right? And then 1 is this point here. So yeah. So where was I? Yeah. So the cylinder, the radius here is each is here. So remember that the area of each one is just the area. Oops, oh my God. It's just the summation of pi multiplied by r2 squared, because that's the larger one, times dx, minus summation of pi multiplied by r1 squared dx, right? And then r2 is just given by, remember, r2 is given by root x. So therefore, summation of pi times root x all squared dx multiplied by dx minus the summation of pi multiplied by, what's r1? R1 is just x squared. X squared squared multiplied by dx. There we go. And then all we have to do is replace this by the integral sign from when they intersect. So that's integration of pi root x squared dx minus integral of 0 to 1 of pi multiplied by x squared all squared dx. So there you go. So this is just like the equation that we showed up here, right? And yeah, so all you have to do is this, and you can pull these out of the equation on each. So if we think of it, oh my God. So if we think of it like this, right? So this is, let's just keep it like that. Square dx minus the integral of 0, 1 here, x squared all squared dx. Then we can think of it like this. All of that of 0 to 1 root x all squared dx minus the integral of 0 to 1 x squared dx. There you go. And then we can just do all the integration here and get the answer, which I believe is 3/10 pi, I think. But yes, that's how it works. So what's the condition for using the washer integration? Washer integration we need to use when when the rotation of axis is like this, and we're splitting the slices kind of like perpendicular, right? You see how we're slicing, like if we have a knife, we're slicing perpendicular to the rotation axis, right? Okay. But what happens when we want to do something like this? Okay, let's think about this. Right? We have something like this. Let's say this is um y equals minus x to the 5 plus 4x cubed. Y equals minus x to the 5 plus 4x cubed, right? Well, we can try, and oh wait, actually, and let's say that the rotation axis is on the y-axis here, right? How are we going to do this? Well, we can try to find the, if we wanted to do the slice method, right? We'd have to find this almost as an independent one, and then this almost as an independent one. But this is just one equation, right? Difference between this and this equation, sorry, and this equation is that these are two equations. But this is a single equation, so it's going to be really difficult trying to find, let's say at point X, right? We're trying to find this height here, that's R1, then we have to go find this height here, which is R2. So what do? Instead of doing by slices perpendicular to the rotation of axis, we're going to use the cylindrical method, and we do this, right? We do it like this. And what this creates is many little um let's say that let's take this one here, right? I'm gonna color it a different one. So I'm gonna say this one, and remember that these are so small that they're basically a rectangle. So we have this one. Let's say this is the slice, right? This is the slice we're working on, and then we rotate it around the axis. This creates a sort of cylinder that yeah, this creates a sort of cylinder, which is similar to what we were doing with the washer. Remember, something like this, right? Except that's just really tall. So in this case, what's going on? We have um what we have is this point, right? Uh okay. What we have is this is the height, right? Actually, let's try to think of this. So, what's the equation for finding because simply the volume of the shape, which is created by the rotation of this around the axis, this shape here, traced by y equals minus x to the 5, is going to be just the sum of all the volumes of these different cylinders, right? We can imagine, all these cylinders, and then like this one here, and then we have a bigger one, right? We have a bigger one here, we have a bigger one here, which is bigger, but the same height. And then we have another bigger one. So it's just the summation of these things. So first of all, we need to find the volume. Let's say this, the volume of the solid is just the summation of the volumes of each cylinder, right? The summations of each of the cylinders. So what's the volume of each cylinder? Well, Um, oh, yeah, let's go back to here. So the volume of the solid is equal to the summation of the volume of each cylinders. Therefore, we can just use the integral sign instead, and we go from A to B, wherever that starts, and then we can do the volume of each cylinder. I just want to show this so you can remember that this sign is no different from the integral sign. Okay, so how do we do this? How do we do this? Well, if we think about it, at any point x, let's say our point x is here. Let's say this is at point x. Then the height, right? The height of this rectangle is given by fx, right? We just plug our x into the equation, which is y equals. So this height here is just the height of the line, and at any point on the line, it's equal to y equals the height is equal to y, which equals to minus x to the 5 plus 4. Let me rewrite my 5 plus 4x to the plus 4x cubed. So if we think of it, instead of point x, it's a, right? Let's say this is point a. Well, then this is just equal. Then the height would just be equal to a minus a to the 5 plus 4a cubed, right? Because the original equation was minus x to the 5 plus 4x cubed. So you just put whatever the point is. So the point is that the height of this equation is equal to the equation, the height of the cylinder is equal to the equation at that point, which is just going to be equal to y, or fx if we think of it. So that's just equal to um, minus x to the 5 plus 4x cubed. Okay? Let's delete this. Okay. So now we have the height. What is the thickness of this? So let's say that we had, if we had R1 here and we had R2 here, what's the thickness here? What's the thickness of the line, right? The thickness of the line, remember, is dx, because the length here we're using is, remember, dx. Remember the last episode. So this is dx. That means R2 minus R1 is equal to dx. Another way to think of it is x is right in the middle of dx. This x here, x is right here. X is right in the middle of dx. So let me make this cylinder super big so I can show you guys. If we have a cylinder like this, and let's say that this was our original rectangle, we work in the plane of this rectangle. So let's say this point here is x. Well, remember that the length of this here, this is worth dx. And so we can say that I'm running out of colors here. Let's use red. this here is so if we think of it like this, so let me say it like this. We need basically for the equation to work, we need R1 and R2. We just need R1 and R2. This is just a washer, but it's tall, right? So we need figures for what R1 and R2 is. And R1, well, if you think about it, let's trace the line here. R1 is to here, which is just here. We know what X is, right? We know what X is. This one. This is X. Well, R1 just happens to be, let's use another color because it's hard to see. R1 just happens to be this length here, all right? From this point to this point, which just happens to be X minus half of dx. Does that make sense? I'm going to erase this rectangle to make it easier to see. But R1 is just R1 is just equal to X, which is this length, minus 1/2 dx, which is this length right here. Right? So then what's R2? R2, and we're taking it from the plane here. So R2 would be here. So R2, well, this length is just equal to X plus 1/2 dx. So now if we have R1 equals X plus R1 equals X minus 1/2 dx, and R2 is equal to X plus 1/2 dx. Now we have a value for R1 and R2, and then we can find the volume of each cylinder, right? So we need the volume of each cylinder. So what's the volume of this cylinder, right? Of any cylinder. The volume of the cylinder is the area on top multiplied by the height, which is equal to, area is equal to this area here, right? This area here is equal to pi r2 squared minus pi r1 squared multiplied by h. And that would just be equal to, let's take the pi out of this equation first, like this. And this would give us, sorry, pi, and then inside the brackets, let's use square brackets here. R2 is just equal to X plus 1/2 dx, all squared, minus X minus 1/2 dx, because that's R1 squared, all that multiplied by h. So let's just do that down here. I'm going to copy it over. So now we're just going to expand it. So let's bring pi and h out here. And then that's just x squared plus dxx plus 1/4 dx squared. All of this minus x squared minus dxx plus 1/4 dx squared. And look at this, x squared minus x squared. That cancels. Let's use blue. X squared minus x squared, that cancels. Dxx minus dxx, which is plus, that turns into 2. So if we write pi here, and then dxx minus dxx, which is dxx plus dxx, 2 dxx, plus 1/4 dx squared minus plus 1/4 dx squared, which is 1/4 dx squared minus 1/4 dx squared. Those cancel. So that's what we're left with. The volume of each cylinder is equal to this. Remember that h is just the fx. Oops, can't write. Okay, x is just fx in this case, and so that's equal to minus x5 plus 4x cubed. Therefore, the volume of each cylinder is equal to pi multiplied by minus, actually, let's just put fx because that's our equation. Fx multiplied by 2 dx. x. There we go. Or I forgot how I put it up here, but yeah. Okay, right? And then remember that the volume of the solid is just the sum of the volume of each cylinder that we've made. And the volume of each cylinder is what we've done. So that's just the sum of pi fx to, I'm going to put x before dx, pi fx, pi times fx times 2x times dx. And we can just rewrite this as the integral sign from the starting point to the ending point of pi fx 2x dx. And there you go. That's how you find the volume of any solid through through the cylinder shells. We're making cylinder shells. So yeah, sorry if I was messing up so much, guys. Well, I just learned this. I just figured this out like during like the last 5 minutes of class. But this is a good way for me to lock my knowledge, lock my memory in, and kind of remember how to do it. So yeah, hope you guys enjoyed. Hope you guys find that helpful. This is the equation here. Um, yeah, hope that made sense. All right, let me just check if there's anything else. So yeah, the volume, just think of it, this idea here, right? The volume of the solid is the sum of the volume of each cylinder. That's so important because that's where we transfer the summation sign into the integral sign. And then we just need the volume of each cylinder. Well, we found that here of each cylinder is here, pi fx 2x dx. So yeah, that's all you have to do. You put it here together, and then now you just put fx into there, and you integrate it, and you find the whole volume of the shape when it's rotated by this. So yeah, okay. Thank you guys so much for watching. Oh, I just dropped.